What is Our Ladies? So Our Ladies is now a global organization with the mission of promoting the R language for empowering women at all user level by building a collaborative global network. It is a gender diversity friendly community founded in 2012 by Gabriela De Quieros in San Francisco, and actually started as just as we are doing now. There are a simple group of people that meet each other, organize events, and then it has grown up nicely all around the world. So Our Ladies is now a worldwide organization with 219 chapters in 16 countries with more than 4,000 events and 93,000 members globally. So I think it would worth it to also have a look at the website at ourladies.org. So before heading to the pool, just a little mention about Our Ladies Room. We are a local chapter of Our Ladies Global, and as well as Our Ladies Global, we are dedicated to promoting gender diversity in the art language. So we welcome everyone who would like to join us. We organize workshops, tutorials, general talks for mostly on art hot topics, but we also talk about books and career. The original founder of this chapter is Claudio Vitolo, she's also a co-founder of Our Ladies Global. Also, I'd like to mention that we are always open to new joiners as a co-organizer of the chapter. So I'll put this Google form in the chat, just in case any of you would like to collaborate with us, or maybe just keep in touch, share some ideas. Okay, so so far so good. We had a busy schedule and we expect much more. We had a variety of events until now, and talking about modeling, infectious diseases, Porto, debugging R. But today we are going to talk about spatial data. And the next month it will be an evening with Hadley Wickham, so very exciting as well. We also featuring very other interesting speakers, and then we will let you know. So stay tuned. We will let you know soon more about that. So I pass the word to my colleague Silvana. Here you have the Slido, and so we do a little. Okay.
Tidy models, Bayesian modeling, agent-based modeling, R and NLP in healthcare. Okay. Targets. Okay, these are all lots of cool ideas. Thanks a lot. Should we move maybe then to the second question that is a little bit more specific, or anyone else? Oh, I see one person typing still in the cloud, so that's good. Statistics. Okay, great. Thanks a lot for all the ideas. Let's move then maybe to the second question. Now the question went away from the screen, but who would you like us to have as a speaker? If you have any names in mind, or maybe a role in an industry or department, someone that you would like to hear, to listen to. If any name comes to mind. be anything in general, right? I mean, role or industry. Yeah, for instance, yeah, GeoHealth. Yes. Bruno Rodriguez. Okay. Ellie Holder. Harvard Root. No Rose. Max Kuhn. Julia Silge. Okay. Anyone else wants to give us any more ideas? Environmental. Okay. Okay, I think this is good. Yeah. Oh, are we getting more? Yeah, people are typing. I'm torn between, I would like to hear more ideas, but I will also like to leave the floor to Paula, which I guess we all want also. So yeah, one of the authors of Production Learning with R. Okay. Sure. Great. Yes. Okay, I'm going to stop it here, right? So we can move. But this was all great. Thanks for the many ideas. Yeah.
Welcome again. It's now time to hand the floor over our esteemed speaker. Please join me in welcoming Dr. Paula Moraga, Assistant Professor of Statistics at the University of Science and Technology, Kaufst, with a Master in Biostatistics from Harvard University and a PhD in Mathematics from the University of Valencia. Dr. Moraga brings extensive expertise in geospatial data analysis and health surveillance. Her research has influenced policy decisions addressing disease like malaria and cancer globally. Dr. Moraga's contributions include developing R packages for risk modeling and disease surveillance and creating educational materials. So let's warmly welcome Dr. Paula Moraga.
So thank you so much for the invitation. It's a real pleasure to be here and be able to speak about my research. So thank you, Federica, Silvana, and Rafaela for all the time and effort that you put in organizing these meetups because they are great. And I'm very happy to be here today. So I'm going to share my screen. Can you see the presentation?
Yes.
Okay, so my name is Paula Moraga. I'm an assistant professor of statistics at King Abdullah University of Science and Technology, known as KAUST, in Saudi Arabia, where I'm also the principal investigator of the Geospatial Statistics and Health Surveillance Research Group. My research focuses on the development of statistical methods and computational tools for geospatial data analysis and health surveillance. I have developed methods to understand spatial and spatiotemporal patterns of diseases such as malaria in Africa, leptospirosis in Brazil, and cancer in Australia. And I've also developed a number of R packages for Bayesian disease mapping, detection of clusters, and risk assessment of travel-related spread of disease. And I'm the author of the books, Geospatial Health Data and Spatial Statistics for Data Science. These books are published by CRC, and they are also freely available online and help researchers develop solutions to health and environmental problems. So this is the outline of my talk today. First, I will talk a little bit about my education and experience. Then I will give an introduction to geospatial data and methods. And then I will talk about statistical methods, software, and disease surveillance applications I have worked on. And finally, I will talk about my current research. So I graduated in mathematics from the University of Valencia in Spain with an Erasmus year abroad at the Johannes Gutenberg University Mainz in Germany. When I finished mathematics, I started working in a technological company developing algorithms for investing. Then I decided to start a PhD, and during my PhD, I started to work in the Registry of Cancer in Spain. During that time, I realized that I didn't have enough knowledge in epidemiology and biostatistics to analyze disease data, so I applied to a very prestigious scholarship to study a master's in biostatistics at Harvard. I also got a fellowship to do a research stay at Harvard Medical School. I participated in the Google Summer of Code, developing an R package, and did a traineeship at the European Center for Disease Prevention and Control in Sweden. After that, I returned to Spain. I finished my PhD, and then I had several academic statistic positions, first at Lancaster University in the UK, then I went to Harvard, to the School of Public Health. After that, I came back to the London School of Hygiene and Tropical Medicine. Then I went to Australia, to Queensland University of Technology. Then I came back to Lancaster again. And before coming to KAUST, I was an assistant professor at the University of Bath in the UK. At KAUST, I lead the Geospatial Statistics and Health Surveillance Research Group. This is a team of postdocs and students that work on the development of statistical methods and computational tools for geospatial data analysis and health surveillance. I started the group 4 years ago, and since then I have graduated one PhD student who is now postdoc at Imperial College London, and I have also mentored 2 postdocs who now work at the University Miguel Hernández in Spain and the Office for National Statistics in the UK. I have taught undergraduate and postgraduate courses in several universities at KAUST, at the Barcelona School of Economics in Spain, the University of Bath, London School of Hygiene and Tropical Medicine, and Lancaster University in the UK, Queensland University of Technology in Australia, and I was also a visiting lecturer in Hawassa University in Ethiopia. I have also been invited to teach over 20 short courses in statistical conferences and workshops around the world. These include the Joint Statistical Meetings in the US, the Royal Statistical Society conferences in the UK, and also in the Institute of Statistical Mathematics in Japan. I have created educational materials that impact learning on a large scale, including my books and tutorials. My first book, Geospatial Health Data, Modeling and Visualization with Arila and Shiny, was published in 2019 and has been translated to Chinese. And it covers how to manipulate and transform spatial data and how to create maps using R. It also shows how to fit and interpret Bayesian spatial and spatiotemporal models using ILA and SPDE, and how to create interactive visualizations, reproducible reports, dashboards, and Shiny web applications that facilitate the communication with collaborators and policymakers. And my second book, Spatial Statistics for Data Science, Theory and Practice with R, was published last year. And it covers spatial data types, retrieval, manipulation, and visualization, and a number of statistical methods and models to analyze aerial data, geostatistical data, and point patterns. And the book includes reproducible examples in environment, ecology, epidemiology, criminology, and real estate. And also last year, I received the prestigious Letten Prize This was awarded by the Letten Foundation and the Young Academy of Norway for my groundbreaking research ambitions towards early detection of epidemics and the design of control strategies worldwide. So this was a little bit about and now I'm going to start with an introduction to geospatial data and methods. So I always start with this map. This is John Snow map of cholera. In year 1854, there was an outbreak of cholera in London. People didn't know how this outbreak occurred because they didn't know how cholera was transmitted. So Dr. John Snow, what he did was to create this map where he put for each of the locations of people that died from cholera, he put a point, and he found out that all the points were clustered around a water pump in Broad Street. So he convinced the authorities to remove the water pump, and when they did that, the outbreak disappeared. So this is one of the first examples on the importance of geospatial methods for disease surveillance. These methods can be useful to understand geographic and temporal patterns, identify potential risk factors, detect clusters, measure inequalities, and also for the early detection of disease outbreaks. And these results can be communicated using maps and other visualizations and guide decision makers to better allocate limited resources and to design strategies for disease prevention and control. In addition, many of these methods are also useful in fields that use geospatial information, such as ecology, environment, or criminology. So in spatial epidemiology, we distinguish statistical data and point patterns. In aerial data, we have that the region of a study is partitioned in small areas, and in each of these small areas, we have the number of cases, population at risk, and risk factors. And the objective is to predict the risk in each of the areas. When we work with geostatistical data, we are assuming that the risk is a spatially continuous surface that can be measured at the specific locations. And the objective is to predict the risk in areas where we don't have data, in areas that are not sampled. And in point patterns, we have that the data are the locations of people that have disease. And the objective here is to understand what is the process that originates this data. Is this data at random? Are they clustered? Are they close to a contamination source? So if we work with aerial data, remember we have a region of a study that is partitioned in small areas, for example, municipalities or states. And in each of these areas, we have the number of cases and the population. And we want to estimate the risk of the disease in each of these areas. So to estimate the risk, we can calculate the standardized mortality ratio, or SMR. And this is equal to the number of observed cases divided the number of expected cases. So if SMR is greater than 1, this means that we have observed more cases than expected. So this is a high-risk area. And if SMR is less than 1, this means that we have observed less cases than expected. So this is a low-risk area. So these values are very easy to calculate. This is just a ratio, but they may be misleading or unreliable in areas with small populations or when we are dealing with rare diseases. So instead of calculating these values, what we do is to use models that enable us to incorporate covariates and to borrow information from neighboring areas to obtain smooth relative risks. So we use models like this. Like we say that the number of cases observed in area I follows a Poisson distribution with mean, the expected counts times the relative risk. And then the logarithm of the relative risk is equal to some covariates plus random effects. So here, the fixed effects quantify the effects of the covariates on the disease risk. And the random effects represent residual variation that cannot be explained by the covariates. For example, if here in the covariates we don't put information to that affects the disease risk because we haven't measured that information or we don't know how to measure that information, all of that variability will be in the random effects. And we can put a spatial random effect to acknowledge that two areas are close to each other. If two areas are close to each other, they may have a similar risk. And also a structured random effect to acknowledge that although two areas may be close to each other, they may have different risk. So if we want to fit this model using R, the first thing we need to do is to calculate the neighborhood matrix. So this is the matrix that tells us what are the neighbors of each of the areas. So, for example, we can assume that two areas are neighbors if they share a common border. For example, the neighbors of area 2 are 10, 3, 65, 63, and 4. And in R, there is a function poly2MB from the package spdep that we can use to obtain the neighborhood structure. So here, for example, we see that the neighbors of area 1 are 21, 28, and 67, and the neighbors of area 2 are 3, 4, 10, 63, and 65. Then we need to fit the model. And to fit the model, we have several statistical packages. For example, we can use ILLA. And ILLA stands for Integrated Nested Laplace Approximation, and is a computational approach to perform approximate Bayesian inference in latent Gaussian models. The syntax of ILLA is very similar to the syntax of the LM or GLM function in R. So first, we need to define a formula with the response variable, the tilde symbol, and the covariates, plus the random effects. And here, the random effects are specified. Then we call ILLA, passing the formula, and it's a computational approach to perform approximate Bayesian inference in latent Gaussian models. So we need to define the formula, then we call ILLA, and then we obtain the results. And then we need to visualize the results. And to visualize the results, we have many excellent packages for static and interactive visualization. And here I'm using Leaflet. So first I define a palette of colors. Here I'm using yellow, orange, red. And then we call Leaflet, passing the map. We add tiles to put a background map to put data into context. Then we add the polygons and the legend. And here we create this interactive map where we can zoom in, we can zoom out, and we can also hover the mouse over the areas to see the information of each of the areas. So now, if we work with geostatistical data, we are assuming that the risk is a spatially continuous surface that can be measured at the specific locations. And what we want to do is to predict the risk of the disease in a continuous surface that can be useful for decision making. This specific example corresponds to prevalence surveys of a disease that is called lymphatic filariasis in sub-Saharan Africa. Lymphatic filariasis is a disease caused by microscopic worms and transmitted by mosquitoes. So when the mosquito bites the person, the worms go to the lymphatic system, and there they cause blockages that cause swelling of the arms and the legs. And this is a disease that is also called elephantiasis. Lymphatic filariasis is prevalent in tropical and subtropical regions of the world, such as Southeast Asia, the Pacific, Sub-Saharan Africa, and also parts of the Caribbean and South America. The main strategy against the disease is mass drug administration. Ideally, we could give the drugs to everyone that needs them, but the reality is that resources are limited and we need to decide which are the areas most in need. So in this example, we had 3,000 surveys of lymphatic filariasis. So in each of these locations, we had a number of people and we tested these people. Some of them were positive for the disease and some of them were negative for the disease. So the prevalence is the number of people positive divided the total number of people in the survey. So here you can see that some locations, for example, in Ethiopia have very low prevalence and other locations have higher prevalence. But we also have many locations where we don't have surveys and we don't know what's the prevalence. So we are going to use the existing prevalence surveys and covariates to obtain a spatially continuous surface of the prevalence that can be useful for decision making. And this is the model that we can use. So in location X, we have a survey where we recruit N people. And out of N people, Y of them are positive. So the number of people that is positive for the disease follows a binomial distribution with parameters N, the number of people in the survey, the prevalence, the probability of being positive. And then we say that the logit of the prevalence is equal to some covariates plus random effects. And here in the covariates, we put characteristics known to affect disease transmission. So this is a mosquito-borne disease. So we can use temperature, precipitation, vegetation, elevation, and so on. And we also put random effects because there will be other factors that we have not included in the model, and all of that variability will be modeled in the random effects. If we want to fit this model using R, we can use ILA and the stochastic partial differential equation approach. And this approach approximates a continuous Gaussian random field with a discrete Gaussian Markov random field using a triangulation of the region of study. So we can use ILA to create this triangulation. Then we need spatial covariates that we can get from different sources. We also have R packages to obtain covariates such as temperature, precipitation, elevation, and then we fit the model. And again, here we define the formula, we call ILA, and then we retrieve the results. And finally, we can also have data that are point patterns. And with this data, we have that the data represent the locations of people with disease. For example, this is the city of Valencia in Spain, and these points represent locations of people that have kidney disease. So these are the locations where they live. So here we can assume that this point pattern has been generated as a realization of a point process. And now we're interested in learning about this point process to estimate the intensity of the events, to identify patterns in the distribution of the observed locations, and also to learn about the correlation between the locations and spatial covariates. For example, we can calculate the intensity of the process. This is the mean number of events per unit area. For example, if we have a point pattern like this, we can calculate a kernel estimate that tell us what is the mean number of events per unit area. And to do that, we can use the density function of the spat-stat package. So this package, spat-stat, is the package that you are going to use if you work with point patterns. So here in the density function, we pass the data, and we also pass a parameter to control the smoothness of the kernel. And we can also specify models. One of the most simple models is the homogeneous Poisson process. And this process assumes that the events are equally likely to occur at any location of the study area, independent of the locations of the other events. So this is to model random patterns. We can also specify models for clustered patterns where points are aggregated, or inhibited patterns where points are separated. And one common process is the log-Gaussian-Cox process that can be used to model phenomena that are environmentally driven. So this was an overview of geospatial data and methods. And now I'm going to talk about statistical methods that I developed for geospatial data analysis and health surveillance. And I'm going to focus on spatial data misalignment. So I'm going to motivate this problem using air pollution, and specifically fine particulate matter, or PM2.5. So PM2.5 are tiny particles that are floating in the air. They come from fires, motor vehicles, industries, and they are tiny. They are less than 2.5 micrometers in diameter. So they can get deep into the lungs and cause very serious health conditions. So it's important that we monitor these levels and take action to reduce the levels if they are exceeded, in order to protect the health of the population and the environment. We can get air pollution measurements from monitoring stations that are placed at the specific locations. For example, here we have PM values in Europe at the specific locations. We can see that we have high values in the east of Europe, the north of Italy, and we also have very low values in the north of Europe. So this information is good in the sense that it is local, but the disadvantage is that we only have data where we have monitoring stations, and we have many locations without any information. We can also get air pollution measurements that are derived from satellites, and these provide a raster grid. So here we have, again, PM values in Europe that are provided in a raster grid of a resolution of 50 square kilometers. So in each of the cells of this grid, we have one value for the air pollution. So this dataset is good in the sense that it has a whole coverage. It covers the whole Europe. But the disadvantage is that in each of these cells, we only have one value. But in reality, air pollution varies continuously in space. So the question is, how can we combine point level data that is local, but is not complete, with area level data that has a full coverage, but is not at the resolution that we would like to be, to produce a spatially continuous surface of air pollution that can be useful for decision making? So we can specify this model. This model assumes that underlying all observations, point level observations and area level observations, there is a spatially continuous variable that can be modeled using a Gaussian random field. So we'll have that the air pollution at the location X follows a normal distribution with mean mu plus s. And here mu is the large scale component of the model. So if we have point data, we will say that the expected value of y is mu plus s. And if we have aerial data, we will say that the expected value of the y in the region B is the integral of mu plus s over the region divided the area of the region. So this model has also been used by other authors, but other authors, they used MCMC for inference. And the consequences of that is that if we have big data set or big regions, the inference could be infeasible. So instead of using MCMC, we're going to propose an approach that uses ILLA and a modification of the SPDE approach. So ILLA, as I said before, stands for Integrated Nested Laplace Approximations, and is a computational approach to perform approximate Bayesian inference in latent Gaussian models. And the SPDE approach approximates the continuous Gaussian random field with a discrete Gaussian Markov random field using a triangulation of the region of study. So if we have observations at these points, we need to put a triangulation on top, and then we can say that the value of the process at location X can be expressed as a weighted average of the value of the process at the vertices of the triangulation with some weights. And these weights are given by piecewise polynomial basis functions on each of the triangles. So, in more detail, imagine that we have a triangle of the mesh, and we have an observation here at the location X. We will say that the value of the process at location X is the weighted average of the value of the process at the vertices S1, S2, and S3 with some weights. And the weights are given by the barycentric coordinates. So they are proportional to the areas of these subtriangles that are formed by the point and the vertices. So we'll have that the value of the process at X is equal to S1 times this blue area plus S2 times this green area plus S3 times this red area. And all of that divided by the whole area of the triangle. And here you can see that if the point is very close to one of the vertices, that vertex will have more weight. But now in our problem, we also have areas. For example, we can have this rectangle or this square, and we will have an observation in this area. So we can say that the value of the process in this area is a weighted average of the value of the process at these vertices that are within the region, these red points. So we have that for both point data and area level data, we can express the value of the process as a weighted average of the value of the process at the vertices with some weights. And the only thing that we need to do is to specify a projection matrix that maps the Gaussian Markov random field from the observations to the triangulation nodes according to the types of data that we use. So using this model and this approach, we can fit the model to integrate data that is available at different spatial resolutions. So we conducted several simulation studies, and also we used the model in a real application, and we showed that the combination of data provides better predictions than just using one type of data. And this is a flexible model that can be extended to many problems of interest. We can include covariates, we can use it in spatial temporal settings, and we can also use it in situations where we have preferential sampling. So we have used this approach for air pollution, but we can also use it in disease mapping. Disease mapping is very important to understand geographic and temporal patterns of diseases and allocate resources in areas that are most in need. But often these maps are given at an aerial resolution because the cases, for confidentiality reasons, are aggregated in administrative boundaries. So here, for example, we have a map that shows the prevalence of malaria in Mozambique. And here we can see that the districts in the north have higher prevalence than the districts in the south. So this gives us an idea of the burden of the disease, but this is not very useful for decision making because in a given region, we only have one value, but in reality, the disease risk varies continuously. So we can use to disaggregate area level data and produce high resolution estimates. And here, in a given region, we can identify locations of high and low risk. And this is much better for decision making to allocate resources in areas of greatest need. We can also have the problem where we want to quantify risk factors using misaligned data. For example, we have a response variable, for example, lung cancer at county level, and then we have covariates at a different resolution. For example, smoking at a state level. So here, if I want to fit a model, it's not easy to do it because the response and the covariates are at different spatial resolution. So we can use the same approach. We can disaggregate the covariates and then link the response variable to the continuous level of the covariates. So here, for example, we use this approach to predict the prevalence of malaria in Madagascar. So we used prevalence in locations, prevalence in districts, also covariates at a different resolution to obtain a continuous surface of the prevalence. And this method can also be used to detect disease clusters. A disease cluster is an unusual aggregation of cases that occur together in a particular place and time. And as I said before, disease cases are often aggregated at an area resolution for confidentiality reasons. So when we apply the clustering methods, we identify clusters that are comprised by multiple areas. So although disease risk varies continuously in space, the clusters that we detect is just a number of areas. So here we are proposing a method to detect clusters of any shape independent of the boundaries. And we are using a method that uses exceedance probabilities from Bayesian spatial disaggregation models. So first, we obtain a risk surface that is continuous, and then we use the probability that that risk is greater than a specific threshold to calculate the clusters. So here again, in a simulation study, we simulated several scenarios with different types of clusters, ellipse, a square with a hole, and 3 circles. We simulated different levels of risk, 1.5, 3, and 8. And then we applied our disaggregation model and other traditional approaches for detecting clusters. And we found out that our model showed high sensitivity and competitive specificity when compared with the existing methods. Here we have an illustration of what happens when we have a cluster that is a square with a hole. The disaggregation model detects this cluster, but the other methods just detect clusters that are comprised by several areas. And the same happens in a real application. Here we are detecting clusters of lung cancer in Pennsylvania. So these are the clusters detected with the disaggregation model. And then the clusters detected with the other methods that are just a combination of areas. So our approach allows us to obtain more sensitive results. So now I'm going to talk about statistical software. I also develop software so my methods can be widely available and provide benefits beyond my own applications. I'm the author of the package Spatial API, and this is a package for disease mapping, detection of clusters, and interactive visualization, and also co-author of a package called EpiFlows for risk assessment of travel-related spread of disease. So in Spatial API, the user can upload the data, can upload the map, and then by clicking some buttons, they can obtain disease risk estimates and detect clusters, and they can also visualize the results using a leaflet map, a time series plot, and also an interactive table. And they can also generate reports with the analysis conducted. I'm also co-author of a package called EpiFlows for risk assessment of travel-related spread of disease. So as you know, infectious diseases may spread beyond national borders. People living in one location can go abroad and infect people abroad, and also people that come to the infectious location for holiday, for example, can get infected, and when they return to their home countries, they can infect people in their home countries. So this package implements a mathematical model that predicts the number of cases that could be spread to other locations from an infectious location, together with uncertainty measures. And it uses information on the number of cases, population flows, lengths of stay, and incubation and infectious period distributions. And in more detail, the total number of infections introduced in a location from another location is composed of the exportations and the importations. And the uncertainty is obtained by sampling from incubation and infectious period distributions. And now I would like to talk a little bit about my current research. I'm very interested in digital health surveillance. Disease surveillance systems are critical to the early detection of epidemics and the design of control strategies. But traditional surveillance systems have a limitation, and is that information is delayed. From the time that the person gets sick to the time the person goes to the doctor, have the laboratory tests, and that information is in the system, it may take a few weeks. So this information is not useful for taking action in real time. Nowadays, we have access to other types of information, for example, social media data, where people chat about how they feel, or Google searches, where people search treatments for their conditions. And this information is not produced for epidemiological research, but we can use it to detect and to understand disease activity levels in real time. We also have access to demographic and environmental risk factors such as temperature, humidity, precipitation, and all of these are factors that affect climate-sensitive diseases such as dengue or malaria. So I'm working on a modeling framework that integrates multiple data sources to produce local probabilistic predictions of disease activity in real time, and also in an interactive dashboard that alerts public health officials when elevated disease levels are anticipated and provide insights about disease drivers. And I'm also very interested in the development of interactive visualization applications for policymaking. These include digital web health atlases of diseases such as cancer, malaria, dengue, and also surveillance systems to monitor diseases in real time. So here we can use applications that include visualizations that allow us to explore data in an interactive and approachable way. For example, using HTML widgets. So we can use time series plots, where we can show time series in an interactive way, or tables, where we can sort the columns or search specific words to show tabular data. And we can also include maps that overlay health data, risk factors, political boundaries, and other geospatial information that is useful to put data into context. And we can put all of these visualizations together in an interactive dashboard or a web application. And these tools will allow us to identify information for specific regions, understand how disease patterns change over time, compare risk between populations, or measure inequalities. For example, this dashboard that was created with Flex Dashboard shows air pollution globally. So here we have a leaflet map that is interactive. We have a table where we show the PM values corresponding to each of the countries, and then we have a histogram produced with ggplot. And then we have a slider here that we can use to filter the countries that have air pollution values within a given range. So if you want to learn how to create this exact dashboard, you can look at this chapter in my Geospatial Health Data book. So this is done with Flex Dashboard, and here I detail. Here I have the complete code to develop this. And here I have a couple of examples of interactive applications for disease surveillance. Here we also used Flex Dashboard to understand geographic and temporal patterns and identify clusters of malaria transmission in Rwanda. And we focused on 3 demographic groups: children under 5, and males and females above 5 years. And this application allowed us to highlight the need for local strategies within the National Malaria Control Program. We also developed Dengue Tracker. Dengue Tracker is a website that provides weekly updates on the number of dengue cases per state in Brazil. So here we present official cases, but as I mentioned before, these official cases come with delay. So we also use Google Trends information, where people search, for example, the word dengue or dengue symptoms or dengue treatment, and we incorporate that information to produce corrected case counts. So we hope that these reports assist policymakers and also the general public in understanding dengue levels and guide their decisions. So to conclude, open and reliable data and analytical tools, as well as collaborative research, are crucial for solving health challenges, achieving sustainable development, and leaving no one behind. Before finishing, I would like to mention that I'm looking for outstanding PhD students to join my research group at KAUST. KAUST is an international university located on the shores of the Red Sea in Saudi Arabia, and all students receive a monthly living allowance, free housing, and medical insurance. So if you're interested in working with me on the development of statistical methods and computational tools for geospatial data analysis and health surveillance, please get in touch. And these are some references about my work on statistical methods, software, and applications, and also my books, Spatial Statistics for Data Science and Geospatial Health Data, that are, as I said, freely available online, and you can use if you are interested in learning more about spatial statistics for data science and health surveillance. And that's it. Thank you very much.
Thank you very much. That was awesome. Thank you. So I'll unmute yourself, all of you, so you can eventually ask her some questions directly. Okay, you should be able to unmute yourself. It would be nice if you raise your hand first, if you'd like to. So we have an idea what is the who asked it first? Yeah, we learned a lot. Okay, we have, does INLA work in the tidy models framework? That is one question.
Well, I don't think so the ILA package has its own functions. What do you mean? That if later the results can be used to be used as an input of some function of the tidy models framework or something like that? I mean, ILA is a separate package, and you feed the model, you get the results, and then if you
sorry, I've just so you're
yeah. Yeah, I was saying that ILA is a separate package and doesn't work with tidy models. So if you work with ILA, you get the results, and then you need to pre-process that results to work with other R packages.
I have one question, just a bit like a sort of personal question. How did you started working with spatial data? Why did you choose? Because I saw that you have a PhD in mathematics and everything. So, what was the reason for focusing on?
So the thing is that like when I was in high school, I decided to study mathematics because it's the course that I enjoyed the most. But then being in the degree, I didn't like it very much because it was very theoretical. So then I decided to do more statistics courses that were more applied. And then like I started to work, as I said, in a technological company. I was developing algorithms for investing using MATLAB. But then I felt that I didn't learn much. So I decided to do a PhD. And in the PhD, there was a project to work in the Register of Cancer in Spain. And in this project, we had information about the people that had cancer in Catalonia, that is a region in Spain. And I started to work with spatial data because we wanted to understand patterns of cancer in Catalonia. And that's how I started, like working with disease data. And since then, in all the universities that I have been as a postdoc or as a lecturer, I have been involved in projects that are related to health and disease data. But it started like in my PhD.
Yeah, it's a very interesting topic. So we have some more questions. Do you have a GitHub repository with some practical examples?
Yeah, I have a GitHub repository. I started, like, for example, the books, I started to write some tutorials with examples on how to fit models, how to create Shiny web applications, how to create Flex dashboards. And I put that in GitHub. But then I put all of those tutorials together in the books. So you can find them in the books. I finally delete them, or I don't maintain those tutorials anymore. So all of that information, I put them in the books.
Okay, and you can find it on paulamoraga.com website /book.
Yes, so this is my GitHub. I have some of the repositories. For example, the Spatial API app, Shiny Web application that I showed. If you want to develop a Shiny Web application like this, I have all the code here. So if you're interested, you can take a look. So I have this. Yeah, and I have Epiflows, for example. I also have it here. I have some packages, and I also have the books.
Thank you. There is a nice, interesting question from, I'm not sure, is it iPhone? Is it some, would you like to ask her directly, maybe? Are you able to unmute yourself?
Yeah. Hi, I'm Hannah from London. Thanks for the interesting talk. Yeah, so my question was around the disaggregation. So, is there a case where it is not feasible? Because I'll be very keen on like disaggregating aerial data to like more finite, like continuous distribution.
Yes, so you need to think what is your application. Like, you can apply the model and you will get some result, but as you say, sometimes it doesn't make sense. So if for example, in my case, if we have malaria, we may think, or if we have air pollution, we may think that this is spatially continuous and it varies spatially continuous in space, so it makes sense that we disaggregate. But if we have other outcomes that are more patchy, maybe it doesn't make sense. So you need to think if it makes sense that there is a spatially continuous process underlying the observation. If it makes sense, you do it. But if it doesn't make sense, like for example, I don't know, if I'm trying to estimate socioeconomic indices and we have a region with very marked inequalities, and we say, like, for example, this municipality is rich and this municipality is poor. Maybe it doesn't make sense that we disaggregate. Maybe it doesn't. They have separated values, and that's it.
Oh, I see. Thanks very much.
Thank you for your question.
Federica, I think you're muted.
I'm sorry. So I was saying we have Gilbert. I don't know if you'd like to unmute yourself. Is asking about if INLA is also available in Python.
So I'm not sure if it's available in Python, but I know that there is. They are working on having INLA also in Python. I don't know if it's ready yet, or if it's only a version that they are using, but it's not released yet. But if it's not available in Python yet, it will be very soon, because I know they are working on that.
Okay, then we have Nicola Papadretti. Would you like to unmute yourself and ask her directly the question?
Yeah, sure. Thank you. Thank you so much for the presentation. I wanted to ask you if when we are working with aerial data and we have like the continuity matrix that it's mainly made by 0 and 1, does it make sense make some weights based on which is the length of the border that they are sharing on, including the overall border?
Yeah, so yeah, thank you. So yes, like there are many ways that we can choose a neighborhood matrix, and in some cases the choice of two areas are neighbors if they share a common boundary doesn't make sense, because, for example, maybe the areas are super big and it doesn't make sense. So there are other approaches that you can use, like based on distances between the centroids, based on covariates, and the one that you are proposing, I never thought about it, but it may make sense. So yeah, so I suggest that you review, like, because I know that there are several papers that compare different approaches using different matrices, and they give some advice on how to choose the neighborhood matrix. And I'm not sure if this is one of they consider, but yeah, it makes sense.
Thank you.
Thank you. Gabriele, would you like to ask her directly? He said, thanks for the presentation. Do you happen to know whether these methods are applied in the climate modeling space as well?
So can you clarify what you mean by climate modeling? Like make projections of future temperature or something like that?
Yeah, most probably isn't it like that.
Gabriele cannot unmute.
Yeah. So like,
Oh,
so the methods that I presented, they are not used for making projections in the future, because this I think these use like physical models that take a lot of variables in the earth. I think they are different.
okay. And so there is another question, maybe. So he said exactly what I meant. Thank you very much. Now we have another question from Rinda. I think, do we still need to check spatial autocorrelation, such as using Morans? When do we spatial analysis? When do we do spatial analysis or modeling? You can.
Yeah. So for example, if we are fitting a spatial model, one approach we can take is to fit a model with covariates, take the residuals, and then check if the residuals show a spatial autocorrelation. And if they show spatial autocorrelation, we can decide to include spatial effects in the model. So this is a way to do it. Or another way to do it is to fit two models, one with spatial random effects, another without spatial random effects, and compare the models directly. Yeah, but I mean, this is a more statistical technique that we can use if we are interested in learning what's the spatial autocorrelation. I mean, it's not strictly necessary. It depends on what are your objectives for the project.
Thank you. Don't seem to see any other questions. Thank you very much. So that was awesome. Thank you for joining us, accepting our invitation. So I love your books, as I said. I did both of them within the book clubs. And I warmly suggest if any one of you is interested to join the data science learning community.io, the slc.io, for joining our book clubs. So we read the books together, and we practice and learn. So I think it's all. I don't know if Silvana has something to say or.
No, just to thank Paula very much for her time and for sharing all this knowledge with us. Yeah.
Yeah, so the same, like, thank you all for attending the talk. And again, thank you so much for all the work that you do, Federica, Silvana, Rafaela. Like, it's great that you are doing these meetups, inviting our people, because this is what makes us learn and make us collaborate. And it's great to have still this community. So thank you so much.
Thank you.